All right, let's dive in and unravel the physics behind one of the most fundamental forces in the universe, magnetism. We're going to start with the really beautiful, elegant dance of a single charged particle in a magnetic field. And then we're going to build our way all the way up to the powerful principles that drive electric motors in, well, pretty much everything.
So here's our roadmap. We're going to start small, really small, looking at how just one particle behaves. From there, we'll scale it up and see how all those tiny little forces add up to create a big macroscopic force on a wire carrying a current. Then things get a little weird. We're going to uncover a totally counterintuitive result about closed loops. And finally, we'll put all the pieces together to understand the rotational magic of torque that quite literally makes our world go round.
Okay, let's get into it. We have to start with the most basic interaction there is, just one single charged particle flying into a nice, uniform magnetic field. How it moves? Well, that's the key to understanding everything else we're going to talk about.
So the path this particle takes is this beautiful helix. And why? It's all about breaking down that velocity vector. The part of the velocity that's perpendicular to the magnetic field, that feels a force that makes it go in a perfect circle. Meanwhile, the part of the velocity that's parallel to the field, well, it doesn't feel any force at all. So it just keeps on trucking in a straight line. You put those two motions together, the circle and the straight line, and what do you get? This awesome helical trajectory.
Now let's put this into practice with a fun problem. Imagine a particle zipping into a magnetic field. At what specific angle, theta, will the pitch of its helix, that's the forward distance it travels in one full rotation, be exactly the same as the radius of that rotation? To figure this out, we're going to have to write out the formulas for both the pitch and the radius, set them equal, and then solve for that magic angle.
And when you do the math, something really cool happens. The formula for pitch has the parallel velocity in it. The formula for radius has the perpendicular velocity. When you set them equal, look at what cancels out. The mass, the charge, the magnetic field strength, it all just disappears. We're left with a purely geometric relationship. The ratio of the perpendicular to parallel velocities, which is just the tangent of our angle theta, has to equal 2 pi. How cool is that? It has nothing to do with the particle itself or how strong the field is.
Okay, so we've got one particle down. We know how it moves, but in the real world, we rarely deal with just one. What happens when you have not one, but trillions upon trillions of charges all moving together, like they do inside a wire?
Right, so this is the core question we need to tackle. We know the force on a single charge, Q. Now we just have to scale that idea up. And since an electric current is really just a whole bunch of charges moving in an orderly way, it makes perfect sense that a wire carrying that current is also going to feel a force, a big one. But hold on a second. Before we even talk about the force on a wire, we have to remember something crucial. It's a two-way street. A current-carrying wire also creates its own magnetic field. To figure out the direction of that field, we use what's called the second right-hand rule. Go ahead and try it. Point the thumb of your right hand in the direction of the current. Now curl your fingers. The direction your fingers curl, that's the direction of the magnetic field lines looping around the wire. And remember the notation. Dots mean the field is coming out of the page at you, and crosses mean it's going into the page. Okay, now we are ready to get quantitative. We're going to derive the precise mathematical formula for the magnetic force that's exerted on a wire carrying a current.
So where do we start? We always start from the basics, right? Let's just look at a tiny little piece of wire. The total force on this segment has to be the sum of the forces on every single charge carrier inside it. So if there are n carriers in there, each with charge q and moving with some average drift velocity, vd, the total force is just n times the good old Lorentz force.
Now just n, the number of carriers, isn't super useful on its own. We need something more concrete that we can actually measure. We know that the total number of carriers, n, is just the carrier density, n, times the volume of our little wire segment. And the volume is just the cross-sectional area, A, times its tiny length, dl. So we can substitute that right into our equation for the differential force, dF.
And now for the coolest part. If you just rearrange the terms a little bit, you see this group of variables pop out. N times Q times A times VD. And what is that? Well, that's literally the definition of electric current, I. So we can replace that whole chunk with just I. We define a little length vector dl that points in the direction of the current, and suddenly everything simplifies down to this incredibly elegant and powerful formula, dF equals I times the cross product of dl and B. Just beautiful.
Okay, so we have this awesome new formula. Let's put it to work on a classic physics problem. You've got a wire hanging in a magnetic field that's pointing into the page. The question is, what current do we need to send through that wire to make it levitate?
In other words, we want the upward magnetic force to perfectly cancel out the downward pull of gravity.
The physics here is pretty straightforward. If we want this thing to float, the forces have to be balanced, right? The upward magnetic force has to equal the downward gravitational force. Using our new formula, since the current and the B field are at 90 degrees to each other, the magnetic force is just I times L times B. We set that equal to mg, do a tiny bit of algebra, and boom, we've solved for the exact current we need.
So straight wires are one thing, but what happens if we take that wire and bend it into a closed loop? The answer is kind of weird and really, really important.
Let's look at this specific setup from the text. We have a circular loop of wire with a current I running through it, and it's sitting in a totally uniform magnetic field B. To find the total force on this thing, we're going to have to integrate our force formula, dF equals I dL cross B, all the way around the circle.
So when you do the math, when you actually carry out that integration, you find something really interesting. The total force on the top half of the loop points straight down, but the total force on the bottom half points straight up. And look at that, they are perfectly matched in size, completely equal in magnitude.
So, what's the total net force on the entire loop? You add the up force to the down force, and you get a big fat 0.
And listen, this isn't just some fluke because we picked a circle. This is a huge deal. It's a fundamental principle of electromagnetism. For any closed loop of current, no matter what its shape is, a square, a triangle, some weird squiggle, if it's in a uniform magnetic field, the net magnetic force on it is always 0.
Okay, wait a second. This brings up a huge question. A seeming paradox, right? If the net force on a current loop in a magnetic field is always 0, how in the world do electric motors work? They obviously move, they spin. What are we missing here? The answer is the crucial difference between a force and a torque.
And this diagram? This is the answer. Look closely. The forces on the left and right sides of the loop are equal and opposite, yeah? So they cancel out, and the net force is 0. But, and this is the key, they're not acting along the same line. They're offset from the center. And what happens when you have two equal, opposite, offset forces? You don't get movement from one place to another. You get a twist, you get a rotation, you get torque.
This torque is the secret sauce of a DC motor. But there's one more clever trick. As the loop spins, that torque would actually reverse direction and just make it wobble back and forth. Useless, right? That's where this little genius invention called a commutator comes in. It's a split ring that reverses the direction of the current every half turn. By flipping the current at just the right moment, it makes sure the torque always pushes in the same rotational direction, giving you smooth, continuous spinning.
So that's the big takeaway here. You have to separate the idea of moving from one place to another, that's translation, and it's governed by net force, from the idea of spinning in place, that's rotation, and it's governed by net torque. Zero net force just means the center of mass isn't accelerating, but a non-zero net torque will absolutely make that loop spin. And that single idea is the foundation of almost every electric motor ever built.
So we've established the what and the why. We know a torque exists. But this is physics, right? We need to know how much. So I'll leave you with this question to chew on. How would you take our force equation, F equals ILB, and combine it with the definition of torque, tau equals R cross F, to derive a precise mathematical expression for the net torque acting on this current loop? Think about it.